Okay, the third type of reaction are oxidation-reduction reactions, also known as redox. That comes from reduction and OX oxidation. So, redox reactions. Now, once again, we need to define what are we talking about here. Oxidation involves the loss of electrons, whereas reduction involves the gain of electrons. So if I have some compound that loses electrons, like say maybe Na, a sodium atom, losing an electron becomes Na+. What's happened to its charge? It's become more positive. Right? It's gone from a 0 to a +1. When that happens, that's called an oxidation. Reduction is just the opposite. Reduction, they gain the electrons. So that might be like a chlorine atom, Cl, gaining an electron to become Cl-. What happens to its charge? It becomes more negative. And so more negative is another way to define a reduction reaction. So oxidation, reduction, and if you think about it, one thing's losing the electrons, the other thing's gaining the electrons. They're always going to be paired up. In other words, one of the things in my beaker is going to lose that electron, the other one's going to gain it, right, to form these redox type reactions. Now in some cases you're actually forming like ions. That makes sense, like the one I just talked about. Other ones, this can actually occur to molecular, that is, they covalent bonded molecules, where we're not going to form ions, yet nevertheless we have an exchange of electrons. And it's going to get a little trickier then to understand those. That later chapter again. Right now we're just trying to classify it and get you to recognize these types of reactions. Alright, so here's the example I just mentioned. Sodium, if it loses an electron, it becomes Na+. We would say that sodium has been oxidized. That's an oxidation. Chlorine, if it gains an electron, it becomes chloride, Cl-. That's a reduction. We would say chlorine here has been reduced. If I write it out like that, where I'm specifically showing the electrons coming on or coming off, those are called half reactions. Half reactions. Of course, you're supposed to write a half reaction in the state that the molecule is usually found. In other words, I don't find chlorine atoms by themselves. Chlorine, just like oxygen or nitrogen or a bunch of those gases, is actually a diatomic molecule. It's always paired. It's Cl2, just like oxygen's always O2. And so, if I was to write this correctly, I would say Cl2 is going to combine with 2 electrons to give me 2 chlorides. Now sodium, being a metal, you do find those atoms by themselves. And sodium, I could write that, goes to Na+ and 2 electrons. Now why do I have 2 in front of these? These are correct half reactions, but if I want to combine this together to give me a full, complete redox reaction, then I have to have the number of electrons be the same. Again, one of them is giving the electrons, one of them is receiving the electrons. Okay, so I have to, if I'm giving away 2 electrons, then I have to accept 2 electrons. If the oxidation has 2, the reduction must also have 2. So that's why I multiply everything through on this sodium one by 2. That way, 2 electrons here from the first will cancel with 2 electrons here on the second part. I can add them all together. Everything on the left now comes on the left for my final redox reaction. So the Cl2 and the 2 sodiums. Cl2, I put my phase, my state symbols here, the gas, and 2 sodiums, that's a solid, a metal in other words. And then everything on the right, my 2 sodiums and my 2 chlorides, well, let's see, they combine together to give me sodium chloride, 2 of them. Right? And that's going to also be a solid until I put in water, right, and it dissolves. But we don't have water going on here. Right? We have just a gas and the solid sodium metal. So there it is. There is my redox reaction. Right? I don't include my electrons in my overall redox reaction because they've just been transferred. They're not being made or created. They were here on the left, they were here on the right. It's the same thing on the left and the right. Kind of like how we did with spectator ions and with the ones above, where if they're the same on the left and the right, we don't have to necessarily include them. So they cancel each other, if you will. And so here's my overall redox reaction. Now what you want to be able to do is take a look at this and say, oh yeah, I recognize this as a redox reaction. I recognize this. These chlorines are not charged. The sodium is not charged. Yet here, they are charged, right? This is an Na+, and this is a Cl-. We must have had an exchange of electrons. Therefore, I can classify this as a redox reaction. Now, what about those ones I mentioned that are not ionic? How could I recognize those as being redoxes. Now again, you don't need to understand them or anything yet, but you need to be able to recognize them. To do that, you have to understand what are called oxidation numbers. Oxidation numbers are easy for ionic compounds. They simply equal the charge of the ion. If you're actually involved with ions, transfer electrons make perfect sense, and the oxidation number is the same thing as the charge of that ion. So chlorine becomes chloride. That chloride is a -1, so it's a -1 for the oxidation number. Right? So why do we need them at all? Because the molecular compounds, the ones with covalent bonds, they don't have ions, and yet we can still get this exchange of electrons in redox reactions. And so what we do is we invent these things called oxidation numbers, which are actually sometimes called pseudo-charges, or you should think of them as pseudo-charges. And here's my definition. In a covalent molecule, what charges would the atoms have if it was an ionic compound? If it actually were ionic, what would it be? I know that's strange. Here's the best way to do it. We've got some fairly short, just 4 little rules here on how to figure out what those oxidation numbers are and how to figure out what those pseudo charges are. Let's go through the rules and then we'll apply them a couple times to make sense of it. Rule number 1. The oxidation number of an atom in an elemental substance is 0. What are they talking about there? Okay, an elemental substance. In other words, it's by itself. It's not bound to something else. It's a pure element. So up here, chlorine. Yep, it comes as a pair. I know it's a gas, but there's nothing but chlorine there. It's by itself. That's what they mean by elemental. And so its oxidation number here is 0. Sodium, again, it's by itself. It's not bound to anything else. 0. Right? So that's what we mean by there. If it's by itself, it's 0. It has no charge. It also has no oxidation number. All right, number 2. The oxidation number of a monatomic ion is equal to the ion's charge. Alright, so again, if it's charged, it just equals itself, what the charge is. So up here, if I've got a Cl-, well, the oxidation number is a -1. In A+, the oxidation number is a +1. So those are easy rules. The first 2 are, almost don't even have to remember them. They're so easy. Number 3, here's where it gets a little trickier, but really not bad. Oxidation numbers for common nonmetals, okay, that's key. So we're talking about things that are way over there on the right side of the periodic table, are usually assigned as follows. Notice the word usually. These are more often than not true. There are exceptions to them. Yeah, just like in solubility rules. Alright, here's the rules. Hydrogen is almost always +1 if you combine it with another nonmetal. It's -1 when you do combine it with a metal. Alright, so we're going to have to go through some examples of that. Actually, let me show you right now. Let's go to a scrap paper. If I have hydrogen and it's connected to a nonmetal, another nonmetal like fluorine, right? What are the oxidation numbers? Well, I recognize fluorine, they like to be -1. Hydrogen would have to be a +1, wouldn't it, in order for that to balance out. That's all they're talking about. If you have hydrogen and it's bound to a nonmetal, then it's almost always a +1. Hydrogen can also bind to a metal as well, though. So you could have something like HNA. Now, when we write it this way, we usually write it in the opposite direction in AH. Why? Because when it's bound to a metal, like in this case, sodium and hydrogen, the sodium is the +1, the hydrogen is the -1. Right? Oxidation state there is -1. Right? So you just have to ask yourself, hey, is this a nonmetal or is it a metal that it's combining with? In one case, this would be -1 for the fluoride, so +1 for the hydrogen. In this case, -1 for that hydrogen. By the way, the names here would be hydrogen fluoride. The names here would be sodium hydride. When hydrogen is a -1, we call that a hydride with that IDE ending. Hydride. Okay. So, back here again. Ooh, that was big, right? When hydrogen is either a +1 or a -1 with either a nonmetal or a metal. Second one, oxygen, almost always -2. It says in most compounds, almost always -2, like in water. All right, water, you got two hydrogens, each one are +1. You got one oxygen, must be a -2. So when you see an oxygen, that's what you go for. Unless it falls into one of these categories. It could be a -1 if you have a peroxide, like O2 2-. Those are not very common, but if you have a couple oxygens kind of stuck together as a peroxide, oxidation state is a -1. Very rarely, superoxides, it's actually a -1/2. That's weird. How can you have a -1/2? Again, keep in mind, these are not true charges. These are pseudo charges. Right? And so a -1/2, it's not like we split an electron. We're just trying to keep track of the electrons because we're going to be transferring them. Right? And we do that with these pseudo charges. And so, yeah, a -1/2, this theoretical pseudo charge, that is okay. Positive values when you're combined with fluorine. So you can actually have oxygen in a positive oxidation number instead of negative. Not very common, but it can happen. Alright, so keep that in mind. Yeah, we do have exceptions for oxygen, but almost always -2. It's always kind of your go-to thing when you see an oxygen. Halogens, so we're talking about fluorine, chlorine, iodine, right? Those things, bromide. Those are almost always -1. Again, there are exceptions, but that's your first thing you should think of. Probably it's a -1. Right? It is -1 always for fluoride. No exceptions there. And -1 usually for the other ones, except when they're combined with either oxygen or other halogens. Alright, so again, we'll have to get some examples on this, and we'll work it out. But go for -1 usually. That's your first guess. Alright. And the last rule makes sense. We've been doing this all along. The sum of all those oxidations have to equal 0. Or if it's a polyatomic ion where the whole thing has a charge, then the sum of them have to equal that charge. It has to add up. So that's almost not even a rule to remember or something. The big ones are pretty straightforward. Alright, let's look at example 4.5. 4.5 here in textbook. To scroll quite a bit away. Here's here example 4.5 coming up here. Okay. Hey, here we go. Assigning oxidation numbers. So H2S. I see this, and one of the rules was hydrogen when it's combined with a nonmetal like sulfur. Hydrogen is going to be a +1. So here, if each hydrogen is a +1, then the sulfur is going to be a -2. Right, and that's again what I have here, hydrogen 2S. So hydrogen sulfide, these are going to be a +1, sulfur is going to be a -2. Right? This is how we usually write the oxidation numbers, by the way, in parentheses. Some people actually don't even use those, but I like to. In parentheses above the actual atoms that we're talking about. Right? Also, notice that with oxidation numbers, I write +1. With charges, I would have written 1 plus. 1 positive, or I've written 2 negatives, 2 minus. But if I'm doing oxidation numbers, -2. That's one way that we help to distinguish whether we're talking about true charges or these pseudo oxidation number charges. Alright, and it adds up to 0. SO3 2-, so sulfite. We've seen that before. Ooh, here it has to add up to be a -2 because the whole thing has a -2 charge. Alright, so what are the oxidation numbers? I'm looking at this. The rule that I remember is oxygen is almost always a -2. And if that's true, because I've got 3 of them, that's a grand total of -6. Now I need sulfur to add up with that -6 to give me a -2, which is equal to the whole thing. It must be +4. Right? Again, if you add that up, a +4 and 3 -2s, that adds up to -2. All right, so here's my oxidation numbers here. +4 for the sulfur, -2 for the oxygen. All right, here's another one. Sodium sulfate. Here I'm thinking, here's my sodium. I know that's kind of group 1. That likes to be an ionic charge. And if you actually have an ion, then the oxidation just equals the charge of that ion. So the sodiums are +1. Sulfates are 2-. And so if I look at just the S and the O4 part, that has to add up to be 2-. And the only way that's going to be true is if my oxygens are -2, as usual, and my sulfur is actually a +6. Alright. Now if you notice, all that adds up to 0 for the whole entire compound. Because I'm going to have 2 of these, so that's a +2. I have this sulfur, which is plus 6. So far I'm up to plus 8. Then I got 4 negative 2s. That's a minus 8. Sure enough, it goes to 0. All right. Let's look at this in the context of a reaction. So here's an example from biochemistry. Glucose. Glucose is C6H12O6. It combines with the oxygen that we breathe in, and you get carbon dioxide and water. Hey, that's a combustion reaction. And sure enough, that's exactly what happens in our bodies in a slightly different sequence of chemical reactions, but the overall net reaction turns out to be exactly the same as a combustion reaction. Just take this sugar and burn it, essentially. Get all the energy out of it. All right, what about oxidation numbers? Let me go with the easy one first. Here's an oxygen. It's elemental. It's by itself. So 0, that was easy. Okay. And over here, here's oxygen. It's almost always minus 2. So I've assigned it to minus 2. That means that carbon must be a plus 4. Here's water. Hydrogen with a nonmetal. So H is plus 1. Oxygen is always minus 2. Sure enough, that adds up just fine. All right, so those are the easy ones. Now what about over here inside of glucose? Well, here we go. Oxygen, almost always a minus 2. So there I put it, minus 2. Hydrogens is with other nonmetals, so it's going to be a plus 1. So far, I've got to get this all to add up, and I've got negative 12 on my oxygens and a positive 12 on my hydrogens. It already adds up to 0. Interesting, right? And so the carbon is actually also in the 0 state, because the whole thing better stay 0 when I add it up. All right, so I've assigned my oxidation states. How does my oxidation numbers, if you will? How does that help me? Well, remember the definition of an oxidation and a reduction. And oxidation is where it becomes more positive. And I look at all my numbers here. I got carbon here that's in 0, and on the right side, carbon is a plus 4. That's become more positive. So I would say my carbon has been oxidized. The carbon of the glucose. Right? Hydrogen, plus 1. Hydrogen still plus 1. All right, so hydrogen's not changing. Oxygen here is a minus 2 or a 0. So it's in two different states in my left side reactants. On the right side, here's a minus 2. So in that sense, like these minus 2s, maybe they stay as a minus 2s, nothing else here. And the water is also a minus 2. So everything's a minus 2. So I got one thing that is changing. This oxygen here. These guys went from a 0 to obviously a minus 2. That's more negative, and therefore the oxygen has been reduced. And it shows up in a couple of different places perhaps. Alright, so there's my pairing. It always is paired. I've got a reduction and an oxidation always happening at the same time. Here's another one. Look at this. I've got zinc plus HCl. Yeah, we know that's an acid, right? Zinc, so I drop it in some hydrochloric acid. What happens? Apparently that reacts to give me zinc chloride and hydrogen gas. I look at that reaction. I might be tempted to say, hey, that's an acid-base reaction, because here's an acid, but zinc, that doesn't look like a base necessarily. I don't see how that fits my definition of base. So, no, this is not a neutralization reaction, really. Right? So I'm thinking, what else is it? It can't be a double displacement reaction. I'm not like swapping partners, because this one doesn't have a plus or a minus. Right? Let's look at the oxidation numbers. Zinc's all by itself, so it's 0. Hydrogen and chloride, plus 1, minus 1. Pretty straightforward. Here, it's an ionic compound, so a plus 2 on the zinc and a minus 1 on the chloride. Here, hydrogen's all by itself, so it's a 0. So those are pretty easy to assign, and now let's look at it. Zinc goes from 0 to plus 2. Oh, it's been oxidized. Hydrogen goes from plus 1 to 0. It's becoming more negative. It didn't quite reach the negative numbers, but it's still sliding to the left on the number line. Right? To the left, which way? In the camera, I'm not sure. Anyway, to the left for me, this way. And if it's going to the left on the number line, that's towards the negative side of the number line. It's more negative. Okay? And so, yep, hydrogen's being reduced. Chlorine, minus 1, state is minus 1. Nothing's happening to chlorine. So this is actually a redox reaction. There, I classified it. I'm getting those changes in oxidation numbers. It's also called a single displacement reaction. Remember before with my metathesis reaction I had what's called a double displacement reaction? Well, here it's a single displacement because I'm only kicking one thing out. See, I used to have hydrogen bound to chlorine, then zinc comes along, kicks it out, and now zinc's bound to the chlorine. the hydrogen's off by itself now, just like before. It was the zinc that was by itself. So this is also called a single displacement reaction. But more importantly, it's a redox reaction. The single displacement would be a subcategory, if you will. All right. Let's look at 4.6 in the textbook for one more example of this. Describing redox reactions. So identify with the equations represent redox reactions. So which ones do? Providing a name for the reaction if appropriate. For those reactions identified as redox, name the oxidant and the reductant. So what gets oxidized and what gets reduced, in other words. So I look at here, carbonate's 2 minus, zinc is 2 plus. All right. Here, zinc is still 2 plus, oxygen is 2 minus. So zinc hasn't changed. Here, oxygen is 2 minus, 2 minus, 2 minus. That's all the same. Carbon, I don't see anything changing. So is this a redox reaction? No. No, it's not. Moving on. Here's gallium by itself, liquid, plus bromine becomes gallium bromide. Gallium's by itself, 0. Bromine's by itself, 0. Here, oh, bromine, that's -1, so gallium must be +3. Ah, that's a redox. Gallium goes from 0 to +3. Bromine goes from 0 to -1. That's a redox. C, H2O2, hydrogen peroxide, going to water and oxygen. Okay, hydrogen peroxide. That's one of those kind of exceptions, one of those sneaky oxidation rules. Like peroxide, the oxygens are actually just in a -1 charge, which gels because here's hydrogen, they like to be in a +1, right? So that adds up to 0. This goes to water, where oxygen's now a -2 and hydrogen's a +1. So hydrogen stays as +1, everything here. But oxygens went from a -1 to a -2. Oh, they've been reduced, more negative. Here it's oxygen's by itself, so it's 0. Here, oxygen's gone from a -1 to a 0. Actually, that's more positive. It's to the right on the number line. And so that's been actually oxidized. So we have oxygen here in my peroxide. Some of them are being reduced. Some of them are being oxidized. Either way, that is a redox reaction for sure. Okay, etc., etc. So you get the idea. Oh, last note. The book has a big section on balancing redox reactions. Right? There's enough in this chapter as it is. We are going to wait on the whole balancing redox reactions until that later chapter when we look at them more closely and in more detail. So for the time being, you can skip the whole idea of balancing them, but be able to assign oxidation numbers, be able to figure out what's being oxidized and what's being reduced, and recognize a redox reaction because of that.